Welcome back to ECE 501B. It's been a while, and we are approaching the end of the semester. You have two homework assignments remaining, homework assignment 7 and 8. Homework assignment 7 is due a week from Wednesday, and we voted before class. If you're watching this and you normally come to main campus, don't come to main campus Wednesday. You won't find anyone in the room at 4 o'clock. So we won't have class on this Wednesday, the Wednesday before our break, but obviously a week from that date you have your homework 7 due. Homework 8 due is the following Wednesday, and deliverable number 1 is due on the day we don't meet. Oh, and I need to remember something about office hours on the 28th. I have to go present, so we won't have the normal office hours on a week from Wednesday, or the Wednesday after the Thanksgiving break. I'm sorry for confusing you. Don't get confused about the final exam. The final exam is on a Tuesday, and it's late. It's at 6 p.m. to 8 p.m., and it will be in this room for those of you in main campus. Today what I want to do is finish the proof. Hopefully you've already watched last week's material. We were absent from class, but it's there available to you, and I think part of that was getting through the proof of polar decomposition. Essentially, can we factor a operator into two pieces? A positive piece that does the scaling, maybe you want to call it a non-negative piece because it can have 0 for its scaling, and a direction piece. Can we rotate? So scale and rotate for a given operator, and that's then called a positive operator and an isometry. You've maybe heard of orthogonal matrices or unitary matrices for real matrices or complex matrices. The book here just says let's use one word and call it an isometry, which is a norm-preserving operator. Once we've finished the proof of polar decomposition, we'll start talking about singular values of this operator T, and those are actually equal to the eigenvalues of a positive operator, which is the unique positive square root of T dagger T. Those are the singular values of the operator T. So if we can construct this operator T dagger T, maybe you'll actually want to just find the eigenvalues of T dagger T and take the positive square roots of those. Those will be the singular values of the operator T. Then we will talk about singular value decomposition, which is Theorem 51 in Chapter 7, which is A is equal to U sigma V transpose. U is a matrix of orthonormal vectors. V is similarly a matrix of orthonormal vectors, and sigma is this diagonal matrix of singular values, and sigma might not be square. A is not in general a square matrix. All of this other stuff, the polar decomposition, is concerned with T being an operator, which if we wanted to think about its matrix representation would be a square matrix. What I'm trying to say is the singular value decomposition is a generalization of the polar decomposition. And we'll look at an example. And that's probably what I will record for you for Wednesday as an example of a singular value decomposition. So if the turkey doesn't put you to sleep on Thanksgiving, that video might. So just a heads up. Don't fall asleep today. You haven't had your turkey yet, have you? Let's look at now the Theorem 45 in Chapter 7, which is the polar decomposition, and I'm assuming that you've seen most of this. And so I'm going to scroll through some of these steps. But given a linear operator t, on this vector space V, there exists an isometry, a rotation, an S, an operator, on that same vector space such that we can create this linear operator t as a combination of a scaling, which is represented by this square root of t dagger t, that's a positive operator, with this rotation. So you can think of an operator as scaling, and I say scaling, but it could be contracting. Scaling could be a contraction. It could be a growth, but it could be either. So now we scale, and then we turn or rotate. That's a way to envision a operator t. Here's the proof in several steps. First, we're assuming that t is an operator that's an element of L of V. And just pick a generic vector v in that vector space capital V. Little v is in the vector space V. Then we can do the following steps. We can look at the square of the norm of TV. TV is just a vector. We can find the norm of that and square it. But once we start thinking about squaring norms, we can think in terms of inner products. So the norm of TV squared is equal to the inner product of TV with itself. That's the very first equality. And now we can start playing with adjoints of adjoints. Since those are so fun, we can think of t as t dagger dagger in the second slot. What does that do for us? Well, that allows us to actually push that operator in the second slot into the first slot using our definition of an adjoint. And that's what the second row allows us to do. That this norm squared of TV, hopefully now you believe, is the same or is equal to the inner product of t dagger t V with V. And that is simply mainly using the definition of the adjoint and the fact that t dagger dagger is t. Now, going back into chapter 7 to find theorem 35 and 36, we can say, oh, t dagger t is a positive matrix, or I should say a positive operator, and for that reason it has a unique positive square root. Meaning we can now split or factor this positive operator t dagger t into two pieces. Its square root, its unique square root. And now we can say then that's using theorem 35 and 36 to rewrite this inner product. We now have the square root of t dagger t operating on the square root of t dagger t, V, inner product with V. And what's the square root of t dagger t? Well, that's a positive operator because we said it's the unique positive square root, and the definition of a positive operator says it's self-adjoint and it has this inner product, but we're now wanting it to use the self-adjoint property. We now know that the square root of t dagger t is self-adjoint, so we can push one of those operators into the second slot. And that's now, however long we are, 2 lines from the bottom in this list of equalities. We now have the norm squared of TV equaling to an inner product of the square root of t dagger TV with itself. And that is the norm squared of that operator or that vector that's in one of those slots. And now we can conclude that TV has the same norm as the square root of t dagger t. So we haven't messed up the scaling. They have the same norms. TV with the square root of t dagger t, v. And that's what this now says. This actually, I believe, is given an identifying equation in the book as equation 46. It equates the norm. Here are the norms squared, but we can take the square root of both sides and we get equation 746. That TV's norm is the same as the norm of the square root of t dagger t, v. And that's the conclusion that we can reach from that set of steps in part of the proof. We're far from finishing the proof, but so far we have concluded that in this polar decomposition, at least, we can find an operator, a positive operator, that preserves the scaling properties of the original operator t. And we've now been able to conclude that this original operator t can have the same scaling as a positive operator, square root of t dagger t. Now we need to show, because remember, this polar decomposition has decomposed this operator t into two pieces. One piece is this positive operator, square root of t dagger t, and we just have shown that we've preserved scaling. Now we want to show that S is a rotation, is an isometry, that it doesn't change scaling, it preserves the norms. So we want to show that S is an isometry, and an isometry, you've maybe never heard of that, but you've maybe heard of orthogonal matrices if you were dealing with fields of real numbers, or maybe you've heard of unitary matrices if you've heard or played with the field of complex numbers. This is now one term that subsumes or keeps those two in it, or as a part of it. So an isometry, if you wanted something to think about, you could say, oh, that's like an orthogonal matrix if I'm dealing with real matrices, or it's like a unitary matrix if I'm dealing with complex numbers. So now what we want to do is actually look at creating this isometry in two steps. One is, first, we don't necessarily know for a generic operator t that the range of t is going to be surjective, that it's going to fill the whole space of this vector space V. For that reason, we need to sort of have a rotation that only worries about rotating on the range space of t, and making this rotation such that we rotate the range of the square root of t dagger t onto where we want it, which is the range of t. We want to make sure that we're going in the right direction after we've done the scaling. And because we may not have a surjective or a full onto mapping, we now are just saying, let's create a map, a linear map, which we will show, but a map S1 that maps the range of this positive operator, square root of t dagger t, onto the range of t. And then we need to sort of grow that into an isometry. If S1 is a linear map, it's not guaranteed that it's going to be full rank or have everything mapped into the entire vector space V. Because of that, then we need to extend it with this additional map, S sub 2, to turn this combination of S1 and S2 into a true isometry S. S can't collapse or do any kind of scaling. It has to have all of its eigenvalues equal to 1. And that's what we want to try to establish now. is this two-step process of showing that S is an isometry. I think in the previous lectures that you've watched, we showed that S sub 1 was well defined by checking the uniqueness of the map. What does that mean? Well, here is the uniqueness step. It said that if we have two vectors, v1 and v2, and we map them through this positive operator, square root of t dagger t, then that must be the same as saying that tv1 must equal tv2. So we need to have this uniqueness of mapping. If v1 goes through the square root of t dagger t, then, and that's equal to where v2 takes us, going through that same positive operator, then tv1 must take us to the same place as tv2. And here's a proof of that statement. First, let's just compare this vector tv1 with tv2. So we'll compare it by finding the norm of tv1 minus tv2. How did we get to the next statement? What's that called? Equals the norm of t operating on v1 minus v2. That's just additivity, right? So that one you can believe. We just showed that t and the square root of t dagger t preserved norm, so we can get the next row. That's our norm preserving expression, and I say see above. What did I say? That was now using equation 46 in the text. So this second row is now just using what we just demonstrated. And now let's apply additivity of that operator, this positive operator, square root of t dagger t. And now what did we assume? Well, we assumed that the square root of t dagger t v1 was equal to the square root of t dagger t v2, so we can say that that has a norm of 0, since the 0 vector has a norm of 0. And since that 0 is equal to what we started with, we can now say that, oh, what was inside the norm, tv1 minus tv2, that must be the 0 vector. tv1 minus tv2 being the 0 vector says that, oh, if we start with this positive operator on v1 equaling the positive operator on v2, then that implies that tv1 is equal to tv2. So we have a uniqueness between this positive operator operating on a vector and t operating on that same vector. Let's now check the linearity of this polar decomposition. And to check linearity, we have two things: homogeneity and additivity. Homogeneity, by definition of how we defined S1, we have S1 applied to this new vector, which is the positive operator applied to AV. Well, now this is how we defined S sub 1, or that's now equal to T AV. But T is a linear operator, so we can pull that A outside of T, that scalar, and now, again, using the definition of S1, we can now say, oh, that's equal to A, S1 operating on this positive operator, square root of T dagger T on V, and looking at the first expression and the last expression allows us to say, oh, homogeneity is true or satisfied. So that's our homogeneity check. Just kind of playing around with our definition and our understanding of homogeneity of the linear map. And now additivity, we do essentially the same thing. We want to apply this positive operator, square root of t dagger t, to v1 plus v2 and then rotate it through s1. Well, this, again, is just our t by definition of s1. And t applied to v1, v2 is a linear operator, so that's t v1 plus t v2. And let's just use the definition of s1 and this positive operator, or this polar decomposition, and voila, we now have additivity of that map or that operator. So this polar decomposition is a linear map. Now we need to show that S is an isometry. I think this is maybe where we made it to in previous lectures. So we'll slow down a little bit and try to figure out how to turn. S is what? Directionality. So now how do we rotate, or is S actually a rotation? Is it an isometry? And what we're going to do now is we will show the following. We are going to show that S1U has the same norm as U for all U, and now we're restricting U to only being in the range space of this positive operator, square root of t dagger t. That's how we're defining S1. S1 is rotating on the, basically the output of this positive operator on a given vector. And so U is going to be coming from that output. And we're going to show this using equation 46, or expression 46, and equation 47. And let me just write down what those expressions are, as we've already talked about 46. But here I'll just write it down again. 46 was what we started today with, saying that the norm of TV was the same as this positive operator, t dagger t, applied to V. That was equation 46. It was norm preserving this positive operator. And 47 is really just how we defined this rotation, this linear map S1. So S1 applied to the output of this positive operator, t dagger t, applied to V, is equal to TV. That's equation 47. So now let's use those to try to verify that S1 is norm preserving on this restricted vectors, or these restricted vectors that belong to the range of this positive operator, square root of t dagger t. So let's start with the norm of TV. Well, we know by equation 47 what TV equals. That now equals S1 square root of t dagger t V, the norm of that. This is now simply using equation 47. Those two are equal, so their norms are equal. But now what I want to do is apply, I can also say that the norm of TV by 46 is equal to the norm of the square root of t dagger t, this positive operator, operating on v. This is now from equation 46. Those two equalities. And now I've squeezed the right two terms to being equal. And what do the right two terms say? Well, now just view this as a u. That's belonging to what? That lives in the range space of this positive operator, square root of t dagger t, and that's what this is. So now we've just shown what we wanted to show, that the norm of S1u is equal to the norm of u by simply using those two equations, 46 and 47. We've now hopefully shown that S1u, that norm, is equal to the norm of u, but what do we know about u? U was only coming to us from the range of this positive operator, square root of t dagger t. So this was true on the range of t dagger t. So we can be a little bit, well, you need to kind of be careful with this next statement, but it's clear if we're saying that these norms are equal. So if we have the norm of S1u equaling the norm of u, what can you say about the null space of S sub 1? Suppose S1 had a non-trivial null space. That means you could have a non-trivial u that would give you the 0 vector when mapped through S1. So S1u could be the 0 vector. But we just said u was not the 0 vector. But now we have the 0 vector's norm is equal to the norm of something that's not non-zero. So that can't happen if this is true. What that says is that this map, S1, is injective. It has a trivial null space on u belonging to the range of the positive square root of t dagger t. That looks like a plus sign. My daggers are suffering, aren't they? They need a vacation. They need a break. So that's supposed to be a dagger. What have I just said? I said that S1 is injective on a restricted domain, and the restricted domain is on the range of t dagger t. If that norm is true, which we just concluded by using those two equations, that S1u is equal to the norm of S1u is equal to the norm of u, that can only happen as long as S1 is injective. It has a trivial null space on vectors in the range of the square root of t dagger t. We clear on that? What does that say? Therefore, the dimension of the range of the square root of t dagger t is the same as the dimension of the range of t. So now we're not changing. We had preserved scaling between the norm of t and the norm of this positive operator. So we're not losing any dimensions when we look at the range of t compared to the range of this positive square root of t dagger t. If that's true, if these two dimensions are equal, what can we say about their orthogonal complements? We're dealing now with finite dimensional vector spaces. And let's say that we had our vector space V is 10. And the range of T, let's say, is 6. Then what's the, the dimension of the range of T is 6. What's the dimension of the orthogonal complement of the range of T? 4. So what we're saying is that that orthogonal complement's dimension of the range of T is the same as the dimension of the orthogonal complement of the range of the positive square root of T dagger T. If these two are the same, and our underlying vector space V is the same dimension, and we're playing with finite dimensions, now we can conclude something about their orthogonal complement. We can now say, therefore, or imply, that the dimension of the orthogonal complement of the range of the positive square root of T dagger T is equal to the dimension of the range of T's orthogonal complement. Boy, I have to be careful now. I can't turn orthogonal complements into daggers. Is that okay? So now we have two new spaces that have the same dimension. Yes?
I understand the S1 is injective.
S1 is injective.
Right, I see that, but why are the dimensions different?
So now we want to find that the norm of TV is the same as the norm of T dagger TV. So now if that's true, then we really can't lose dimension between T and the positive square root of T dagger T. If we could, then we could find a V that somehow was not giving us the same norm when it went through the positive square root of T dagger T as when it goes through T. So now we have these two. Does that help? I'm sorry, I didn't repeat the question, but the question, I believe, was, where did this come from, this bottom line? How can we conclude that these two dimensions are the same? So now I've tried to explain that, why these two dimensions are the same, and if we're dealing with finite dimensional vector spaces, we can now say that the orthogonal complements of these two share the same dimension. Well, if we now have these spaces, we can now find orthonormal basis on those spaces. So let's now do that. Let's now define, or therefore, orthonormal. Since we have inner products, we can normalize the basis. We have orthonormal, so they're orthogonal and they've been normalized to a length of 1. Therefore, orthonormal basis on the range of the square root of T dagger T, its orthogonal complement, and the range of T's orthogonal complement have the same size or dimension, or have the same length. Let me say have the same length. In our example, I think we said they had length of 4. So now we have a and the basis vectors may not be the same. These are two different potential vector spaces, meaning the range of t dagger t has to be rotated to get us to the range of t, and so now the orthogonal complement of those two ranges, we're going to have some rotation to maybe align them. So the orthonormal basis vectors may not be the same. Phew. So let's choose two different basis vectors, orthonormal basis vectors, for these two subspaces. So now let's choose E1, E2, up to E sub m, where m before we said was 4 in our example. Let's look at that one being the basis on the first one, the orthogonal complement of the range of the square root of t dagger t. And let's choose another. How many of these do I have? Another orthonormal basis on the range of, or the orthogonal complement of the range of t. It has to be m as well. So now we have f sub m on the orthogonal complement of the range of t. So now we have an orthonormal basis of dimension m, we said 4, on one of these spaces, and we have another orthonormal basis, same length, on the orthogonal complement of the range of t. Let's define a new map that basically maps these e's into f's. We just have 4 vectors, and we want to rotate those into 4 other vectors is really what we're doing. We have m vectors, and we want to now rotate those without changing any scaling to get to these other 4 or m basis vectors. And the rotation that we're going to use is going to be s sub 2. We've already used up the 1, s sub 1, to map the range of the square root of t dagger t into the range of t. So now we need to map or rotate on the orthogonal complements of those. So let's define another map. Which we are going to call s sub 2, and let's just have it operate on a generic vector in the orthogonal complement of the range of the positive square root of t dagger t. Whew, boy, that'll put you to sleep better than that turkey will, won't it? Did you know chicken has more tryptophan than turkey? Just to random. All right, this is not 503, but let's get into, this is 501b. S sub 2 applied to some generic vector in the orthogonal complement of the range of t dagger t. So it's some linear combination of these e's. And let's say that it's a1 e1 plus a2 e2 up to a sub m e sub m. And let's say that is equal to, or we're going to define the map S sub 2 such that that takes us to an A1 F1 plus an A2 F2 plus A sub m F sub m. That's how we are defining S sub 2. And what does that mean? Well, S sub 2 is now a map, a rotation, from the orthogonal complement of the range of the positive square root of t dagger t to the orthogonal complement of the range of t. That's S sub 2. So that's taking this m-dimensional set of vectors, this list of m vectors, rotating it into another list of m vectors. And the weighting coefficients, these a's, are the same. So the weighting coefficients A1, A2, A sub m are the same. Or really, what does that sort of mean? Well, that really just means that S sub 2 E, let's say L, is equal to FL. That's really all that we're saying for L's going through the M's. Since the A's are the same on both sides of the equality sign, we're really saying that S2E1 is F1. S2E sub 2, we're going to map that to F2. That's really what we're saying. So now we've defined this rotation, this S2, on this leftover vector space. It was left over. Why? Because maybe the range of T didn't fill all of capital V, all of our original vector space. That's why we have this leftover. That's why we have S sub 2. S1 might just map a part of V or rotate part of V around. So now let's see what we have, or what we can conclude from this definition. We've had a lot of luck with using norms. So let's use a norm again. Let's compare the norms of this left side and the right side. Since the left side equals the right side, by definition of S sub 2, that's how we're rotating or selecting S sub 2. Let's use that to our advantage, or let's just use it and see what we can conclude. From the definition, of S sub 2, we can now say that the norm of S sub 2 operating on A1 E1 plus A2 E2 A sub m E sub m is equal to, let's square it since that usually is cleaner anyway. So let's square that and say that by definition of how we defined S2 must be the same as the norm squared of A1 F1 plus A2 F2 up to A sub m F sub m. That norm squared. Okay, what's this right-hand side's norm in terms of these weightings, A1, A2, A sub m? It's the absolute value of A1 squared plus the absolute value of A, because these F's are orthonormal vectors, basis vectors. So this now is equal to, and this is, I hope I have that's some proposition in an earlier chapter. I'm saying it's 25 in chapter 6. That now says that that right-hand side is actually equal to the absolute value of the first weighting scalars squared plus the absolute value of A sub 2 squared etc. But now, suppose I called this vector W. What can I say about the norm squared of W? It's exactly what I just wrote down, isn't it? Because it's a linear combination of orthonormal vectors. They're not the same as the F's. They're E's, but they're orthonormal, but they're weighted the same. And so the norm squared of W has to equal that sum of absolute value of scalars squared. hope I said the right thing. But that equation. So this is the same as the norm of w squared. Huh! What have we just shown? I don't know. What have we shown? I'm so confused on no. What do we have? We now have the norm of S2 applied to W equaling the norm of W squared. That's going back to the isometry definition, isn't it? This is now saying, therefore, we've now can say that S sub 2 applied to W, that norm is the same as the norm of W. And where is W? Where does W come from, or where does it live? Where's that vector? That was on this orthogonal complement of the range of the positive square root of t dagger t. That's where these e's were our basis vectors. So W belonged to or came from the orthogonal complement of the range of t positive square root of t dagger t orthogonal complement. And now what can you tell me about S sub 2 relative to its null space? If this norm condition is true, what can you tell me about vectors W and this rotation S sub 2? Remember, S sub 2 is rotating from the orthogonal complement of the range of the positive square root of t dagger t into the orthogonal complement of the range of t. Is its null space trivial on that range space? So it's injective, isn't it? And so it's actually an isometry on that restricted set of vectors. So let me just make that conclusion. S sub 2 is injective and an isometry restricted or on this restricted subspace, this orthogonal complement of the range of the positive square root of t dagger t, on the range of the positive square root of t dagger t, its orthogonal complement. Whew. Now we have an S sub 1 and an S sub 2. And we can put them together because what? They were operating on vectors that were in we've orthogonally decomposed our vector space V. And S1 operates on one of the pieces, S2 rotates on the other. So now we have this connection, and we can build our isometry, the total isometry of S that operates on the full vector space V out of these two pieces. That's what I'm going to try to say now. So now let's define our full-blown operator S. Now define operator S. That is S1 is a map on the range of the positive square root of t dagger t, and S sub 2 is a map on the orthogonal complement of the range of this positive square root of t dagger t. And those are orthogonal to each other, aren't they? Those spaces. So now, because there is a direct sum, because there is a direct sum relationship between the range of the positive square root of t dagger t and its orthogonal complement, any vector v in our original vector space capital V can be written as a direct sum decomposition. This little vector v can be written as v is equal to u plus w, with, let's say, u belonging to the range of the positive square root of t dagger t, and w living in the orthogonal complement of that range. So that now we can define our big isometry S. S is a linear combination of S1 on vectors u and S2 on vectors w. Meaning, if you now wanted to say, oh, I'm going to now rotate a vector v through S, well, now we're going to really build S in two pieces. We'll take one piece from S1 and rotate u through S1, and we'll take another piece that's in the orthogonal complement to u, which we said is w, and anything in w we will rotate with S sub 2. And that's now going to be our full isometry S. So now consider S square root of t dagger t v. That's what we want to be our polar decomposition of this original map T. Or we can now say that S applied to the positive square root of t dagger t applied to V. Now where is that vector? It's in the range of that positive square root. So this is a vector in the range of the positive square root of t dagger t. And we know that that is now on this restricted setting. This now is the same or is equivalent to S1 applied to that same vector. But how did we define S1 to begin with? S1 applied to the positive square root of t dagger t v was capital T, our original map. So this is now t v. And this decomposition works for all vectors v. We didn't say where v was coming from to begin with. It was from our big vector space, capital V. So this decomposition works for all v in our underlying vector space, capital V. But now, is S really an isometry? That's the question. So let's see if we can show that in fact S is an isometry. And what does that mean? It needs to preserve these norms, doesn't it? But is S an isometry? So now let's look at the norm of SV squared. Well, we just defined S to be a orthogonal decomposition of S1U and S2W. So let's now say, well, that needs to equal the norm squared of S1U plus S sub 2 W squared. But why are we working with squares of norms? So we can apply inner products, right? So now, can you write that equation in the form of an inner product? Yes. That's now the inner product of S1U plus S sub 2W, inner product with itself. So this is now S1U plus S sub 2W. Now we just get to shuffle these around, right? We now need to apply linearity to this mess of an inner product. Break it up into just having one vector in one slot and one vector in another. Meaning, we have 4 different ways of doing that, right? We can combine S1U with S1U. Let's do the FOIL. This is like a quadratic, or a plus b quantity squared, sort of. You learned FOIL in middle school somewhere. First, inner, outer, and last. No, I didn't either, but I've seen it used now, so I thought you guys had probably seen it. Let's do the L. Let's do the last. You're going, what? He's still worried about his turkey and aluminum foil. No, it's supposed to be a way to remember how to multiply things out. Anyway, the last one is S2W, S2W, inner product. And now let's, I don't know, forget oil. Let's now just do the remaining 2. We have S1U with S2W, don't we? And we have S2W with S1U. And that should give us all that we need. But what do we know about U and W relative to each other? They're orthogonal. So U and W are orthogonal. And what do we know about S1 and S2? On their domains, they have a non-trivial null space, so they are isometries on the restricted domains that they're defined over. So as maps, they are isometries over their restricted domain. So and S1 and S sub 2 are isometries over their respective domains, and because of that they preserve, what do they preserve? They preserve orthonormality, actually. So if you give me an orthonormal vector and I operate on it with an isometry, or you give me a list of orthonormal vectors, I operate on all of those with an isometry S, that second list will be orthogonal. So, and preserve orthonormality. Theorem 42. So if that's the case, if S1U, if U and W are orthogonal, and S1 and S2 preserve this orthogonality, what can we say about this piece and that piece? The vectors in those two slots are orthogonal, so that goes away. And we're left now with the norm squared of SV being equal to these first and last inner products. Or we can now say, or conclude, hopefully, now we can say that the norm squared of SV is equal to S1U norm squared plus S2W norm squared. But what do we know about S1 and S2? I keep harping on this, but what do we know about it? They have non-trivial null spaces on those restricted domains, don't they? So S1 and S2 are norm preserving, or are isometries on their domains by the way we built them, by construction. If that's the case, then we can actually, let me just write it again. We have SV squared is equal to S1U norm squared plus S2W norm squared. If S1 is an isometry on its restricted domain, which U belongs to, then isn't that going to be the same as that? And isn't, S2 likewise will give me the norm of W squared. But now, what did I know about U and W to begin with? They were orthogonal, and they were coming from two different places or two different bins to produce a V. So this is now, since they are, we can use Pythagorean Theorem. A squared plus B squared is really equal to V squared or C squared. And now what have we shown? We've shown that S, the norm of SV, is equal to the norm of V. S is an isometry. So now we can say, therefore, is an isometry. Are you kidding me? Oh, we have an infinite amount of time. If you look at the clock, the server's down. So what have we concluded? We now have done a polar decomposition of a generic linear operator. Let me try to write that down. So any linear operator can be decomposed. Whoa, better be careful here. I'll lose everything. Talking about decomposing, they didn't like that, did they? So any linear operator can be decomposed as a product of an isometry and a positive operator. And we know what those do. We know the positive operator scales, expands or contracts. And the isometry, that just rotates. So now any linear operator we can think of as an expansion and contraction at the same time in different directions, and then a rotation. So we can understand how these classes of operators work. So we can apply that understanding to gain knowledge of any general operators. Now we have these two different pieces or operators that we've separated a linear map into. A scaling piece and a rotating piece. And the bases that we use for those may not be the same. So note that basis, that's supposed to be the plural of bases. Note that bases, where these operators have nice representations, or where they might be diagonalizable, note that bases where these operators have nice representations may not be the same. What we've done can also be viewed as a statement about matrix factorization. Meaning any square matrix can be factored into two matrices. We were talking before about maps, not matrices. So now we're sort of switching gears and saying, look at the matrix representation of those maps. So now we can think of this now as a matrix factorization. Any square matrix, since we were talking about T being a linear map on, an operator, a linear operator, now we can look at the matrix representation of those operators, and that corresponds to square matrices. So any square matrix can be factored into two matrices. One matrix factor has eigenvalues with magnitudes equal to 1, And that particular matrix factor is associated with our rotation, and the other one is our scaling. So now the one matrix factor has non-negative. This was our positive, or this corresponds to our positive operator, has non-negative eigenvalues. And that's our scaling. Now, in this polar decomposition, where we had this two-piece decomposition, the positive operator which we represented as the positive square root of t dagger t is important because that gives us our scaling. So in polar decomposition, the positive operator is this positive square root of t dagger t. And we're now going to basically define singular values. We call the eigenvalues of this positive square root of t dagger t, the singular values of our original linear operator t. And since this positive square root of t dagger t is in fact a positive operator, then we know that the singular values of t are always non-negative. We don't have any negative singular values. So the singular values of our linear operator t are always non-negative. Pardon? No, the question was more than zero. It's non-negative. We can have zero singular values. We can have singular values that are zero. And singular values are nice because they allow us to, if we had three singular values that were, I don't know, 5, 7, and 12, and then the other singular values were 10 to the minus 6, 10 to the minus 7, we'd probably just set those to 0 or say those are basically 0. Let's neglect those. So we then would have fixed a couple of singular values to be at 0. It gives us nice numerical properties, these singular values. We also want to make one more comment, is that these singular values need to be repeated, or can be repeated. We repeat each eigenvalue of these positive square root of t dagger t based on the dimension of the null space of the positive square root of t dagger t minus lambda sub I, capital I, times. So we find the dimension of this, and maybe that's m sub I. Then we would have that many repeated singular values. So little m sub I could be 2. Little m sub I could be 3. If m sub I was 2 and the singular value corresponding to the eigenvalue of this positive square root of t dagger t was 20, then we would have 2 singular values equal to 20. Likewise, if we had m sub I equal to 3, then we have 3 singular values of our linear operator t having the same value. Now let me just say, I don't know if I'll do this tonight or some other time, but you might look at example 50 in chapter 7 relative to finding or computing singular values. I might do that, I may not, but we will get into singular value decomposition so that you can enjoy that either before or after your Thanksgiving break. We'll pick up after that, which basically is generalized eigenvectors, after the break, in a week. Enjoy your break.